So in the cyclotron, what happens is you have some kind of a metallic body like this, and we call this as D. So to begin with, we put a charged particle here. Okay. So if this is, for example, let's say this is plus. Okay. So this is positively charged. So to begin with, this will be, let's say this is negative. Right. So if you have a positively charged and there is some negative charge here, right? Here. So what do you think will happen? Repel, plus and minus. Yeah. So this is negative, this is plus. That means it will attract, right? So as soon as it attracts, it will have a velocity, right? So that means it's going to fly with certain velocity, right? And this entire system is sitting inside a magnetic field, which means this is into the magnetic field. So as soon as it goes in, right, all these things, this entire area is filled with magnetic field, right? So we don't have to show the entire things because we need to draw something here. So look at this. So this is 90 degree, right? Sorry, this is velocity is this way. The magnetic field is into the paper on the board, right? So what did we say? B cross B. So start with B cross B, which means going into the magnetic field. So I'm turning it like this. So look at my thumb. So the force is going to be acting this way. So that means it's going to experience some force, but it will start going like this. And maybe I'll draw this a little bit lower. So it's going to be here. So if I send a velocity here, so B cross B goes this way, so it's going to experience a circular motion. This you already know, right? Because if B and B are perpendicular, it will experience a circular path, right? But one thing what I didn't tell you is the electric field is only in this region. Not inside the D's. This system is called, this metallic body is called D. D's, this and this. Okay. Then call it as D1, D2, something like that. So what this sentence means is, the electric field is only here, which means it's going to get accelerated with certain velocity. So as soon as it enters here, there is no electric field, there is only magnetic field. So if it is only magnetic field and the velocity, what will happen? It will take a circular path, right? If there is some electric field also, then there will be a different path, right? So you want only the magnetic field and some velocity. So the reason why you are giving electric field is to accelerate it. So initially pull it with certain velocity. Are you following what I am saying? Okay. So after this it will be going at certain velocity, and after this it will take a circular path because of the magnetic field of B. But as soon as it comes out here, right, what do you think will happen? It is experiencing the electric field, because in this region you have electric field. And in addition to this, we are doing one more system here. It's called oscillator. So what that means is, as soon as it comes out here, we said initially this is negative, but when it is out here, we are going to say this is going to become negative. So earlier this is positive and this is negative. Now this is going to become negative, this is going to be positive. So that's why we call this system called oscillator. So it just keeps oscillating very quickly. Okay. So even our alternating current is your nothing but an oscillator, right? It oscillates at the frequency of, what is the frequency? 50 Hertz, right? In 1 second it is oscillating 50 times. 50 pluses and 50 minuses, right? So in this oscillator we are talking about like very huge frequency, something in the order of millions of frequency. Okay. Let me check the correct number, but I think it is millions of frequency, in the order of millions. So let's say high frequency oscillator. In the order of millions of hertz. Okay, so it's really huge. What do you mean by oscillator? It oscillates between plus and minus. Okay. So as soon as this comes out here, right, this is going to be positive. Sorry, we said this positively charged, so this has to be negative. So this is positively charged particle, right? If this becomes negative, what do you think will happen to this? It will be attracted, right? So it will go accelerated further. So initially it was having certain velocity, now it is going straight, so it's going to be even more bigger, so it's higher velocity. Compared to this is going to be having higher velocity. Okay. Yeah, meaning higher than this value, because it is getting attracted by this one, so the velocity is going to increase. Right? These means this arrangement, metallic arrangement, so it's something like a shield. So inside it you have magnetic field, but here I think, let me double check it. So I think in the gap you will not have magnetic field, so let me double check that. So maybe in the book they are shown it a little bit closer. So it's going to take a path like this. So what will happen is, by the time it just comes in here, again it will be acted upon by the magnetic field here, right? So in the magnetic field with the velocity, what will happen? It will again take a circular path. But you see now the velocity is this way, right? So B is going this way and B cross D. So look at this. So D is this way, curling fingers, and then going into the magnetic field. So look at my thumb. So the force is going to be this way, which means it will take a curve like this. As soon as it comes out of this, again this will become negative, so it will keep on oscillating. So that means again it's going to get attracted. So again it will go like this. Right? So it's going to take a spiraling path, until the velocity is high enough that once it comes here, I will be firing it. So let's say there is something called deflector here. There is some system called velocity deflector. So instead of going in a straight path, instead of going in the circular path, try to push it in the straight path. So basically what we are trying to do here is, you take a small positively charged particle, something like proton, right? So you put it here, it is not at all moving, right? But how to get the required velocity? Let's say you want to do some nuclear reactions, right? We are going to talk about this in the later chapters. So when you want to do some nuclear reactions, the particles should be coming at very high velocity, only then it can enter into the nucleus, right? Because the nucleus is going to repel the proton plus, right? So you have to have more energy to fire into the nucleus. So that means it has to be going at very high velocity. So how to get the very high velocity? For that we are using this system called cyclotron, or the equipment called cyclotron. So initially we said it is a stationary proton. The moment you start switch on this equipment, it's going to do this. So it will keep on increasing the velocity until you need the required velocity, and then it will be fired into the target. So you can take down this as a target. So wherever you want to hit it, you can just hit it. That's what I said, nuclear reactions. right? If you want to target some, element and then you want to, initiate a nuclear reaction, then you can do that. Yeah, in a way it is like that. Only thing is proton, right? Proton are subatomic particles, which can be slowly increased in velocity until it just comes out to a very high velocity and then shoot it out. So let me do this one more time. So this is not easy, right? Oscillator means it will keep oscillating between plus and minus. Okay. So when you are here, this has to be minus so that it will get attracted this way. When it is here, this has to be minus. So that means by the time it finishes half circle, this should be minus. So meaning this frequency of this particle going around this circle should be equal to the frequency of this oscillator, right? By the time it comes out here, if this is not minus, right, if this is plus, it's going to get repelled. Instead of getting attracted, it's going to get repelled. Are you able to follow what I'm saying? So this frequency of changing, right, how quickly it is changing, should match with this frequency, right? But earlier did we talk about something called frequency, time period and frequency for circular motion, right? That's what we are going to make use of here, right? So we are going to say that frequency should be matched with this frequency. So right now we are talking only about the construction and working. So the mathematical part we are going to do that. Mathematical part is very easy because it's very similar to what we already done, okay, in the previous class. So how come it is so very important question? How come it's not going in a continuous circular motion? How come it's taking a circular path? I mean spiral path. Force. Velocity increases means radius increases. Very good. So that's the answer. So they may ask you a conceptual question. What is the important principle? Okay, so take it down. What is the important? I think that's the first part of the question. What is the important principle the cyclotron is based on? As velocity increases, the particle takes a bigger radius, keeping the time period constant. Keeping the time period constant, so the frequency also remains constant. To go around 1/2 of the circle is T/2. T being the time period. So if I say time period is for one full circle, right? So for half circle it will be T/2, right? As simple as that. So I think we already derived something like, from F is equal to mv squared by r, right? So it's the same derivation, mv squared by r is equal to qvb. So if you cancel this, I will get v is equal to q bar by m. So if I want r, it will be vm divided by qb, right? So all these things we already did. So if I want time period, I can say time period is equal to 2 pi r divided by velocity. So 2 pi r divided by velocity is q bar by m. So r cancels. So 2 pi m. So 2 is equal to 2 pi m divided by qb. So nothing new. Whatever you already done, same concept. So if I want the frequency, frequency of the cyclotron. C stands for cyclotron, right? So QB divided by 2 pi m. Frequency is nothing but 1 by P. So it becomes the reciprocal. So in order for this system to function, what is the important criteria? The frequency has to be matching, right? By the time it comes out here, this has to change exactly, right? If it's not changing at a particular instant, everything will be collapsed. If this is plus, plus and plus will repel and it will not be coming this way, right? Exactly when it is out here, it has to be changing to minus. So that thing is very, very important. So we say the mu C of the cyclotron should be equal to the mu C of the applied voltage. So this is cyclotron, this is the applied voltage. So applied voltage of the, what can we say, oscillator. Okay, is this clear? If this is not the case, then you are not going to have a functioning cyclotron. It's not going to be useful, right? So you have to adjust this until this is matching this one. So this condition, whenever you say something like one frequency matching another frequency, we have a special name for that. What is that? Resonance. Yeah, very good. So it's called the resonance condition. So this is called resonance condition. Okay, very often you will hear the word resonance. So what do you mean by resonance? One frequency matches another frequency. Huh? Frequency of the object. Okay, little more accurately, it's very close. So every system has got a frequency, right? So I think I must have shown you many times, but I can show it one more time because there are some other students, new students. So you take this scale, right? So you just vibrate this. So you take it like this. That's a vibration. It has got a frequency, right? You push it, you change the length, the frequency changes. Are you able to follow what I'm saying? So depending upon the length, it has got a natural frequency, right? When the driving frequency, meaning if I push something, right? So if I'm hitting it, so when this is, so let's say it is doing, and at the same time if I keep hitting, right? That is my driving frequency. When this driving frequency matches the natural frequency, we call it as resonance. Okay. So if you want, I can give you one more simple example of resonance, which is very easily seen in pendulums, right? So depending upon the length, right, the frequency will change, right? So let's say this is natural frequency, right? Yesterday we measured the time period, right? From that you can calculate the natural frequency. So when this is going like this, right? Let's say the child is, playing in the swing, right? And you want to go and push it, right? So if you do it like this, do you think the child is going to be happy? So you are pushing it in a very awkward manner. So it's not matching with the movement of the swing, right? So instead, if I did like this, what do you think will happen? Child will be going higher and higher and the child will be happier, right? And that is what we mean by resonance. Of course, I am not doing it correctly. So this frequency is matching with the pushing frequency or the driving frequency is matching with the natural frequency. When that happens, it will be going at maximum amplitude. Are you able to follow what I am saying? So when the swing is coming towards you, if you keep pushing it immediately, then it's going to reduce the amplitude. It's going to slow down very quickly. Whereas when it is coming up here and then it's ready to go this way, that is the point when you are supposed to push. So which means this natural frequency should match with your driving frequency. If that happens, you will get the maximum amplitude, right? So that is what is called resonance. Okay. In this case, it's not exactly the same, but still we call this as resonance condition. Okay. So I hope you have some idea about resonance, because very often you are going to be studying about resonance. Okay, one more small thing and we are done. So one small equation, and that after that I am done. So that is the resonance condition, and then we are going to say, what do you think will be the velocity? How do I calculate this velocity? Do you know formula for velocity? V is equal to q bar by m. Q is not going to change when it is going around like this. Mass is not going to change. Magnetic field is constant. So what is changing? R. So if I know the R value, which is the maximum R here, then I can find the velocity with which it is coming out. So that means take it down. So from the center, if I say this is my R, right? R value, capital R. So let's call it as capital R. The small r is something like a variable, it keeps changing. The capital R is something like a constant, right? So, V is equal to q bar by m. But in this case, the maximum radius is going to give you the maximum radius is equal to R. So the V max. So if you have trouble reading that, let me write it here. So people in the back so that they can also see it. So I said V is equal to q bar by m. V max is equal to QBR divided by m, because this is the maximum radius. So in the question, if they ask you how to find the highest velocity with which the cyclotron is, throwing out the particle, right? Then this is the formula you will have to use. And then yesterday itself, I think we used one more condition, which is kinetic energy is equal to half mv squared, right? So if you want to find the kinetic energy with which this is coming, you should say V max. So half m V max, half m q bar by m the whole square. So mm cancels, so I get q squared, v squared, r squared divided by 2m. That's all. So that's your kinetic energy. So it's exactly the same thing what we did yesterday, right? The previous class. But here you are saying it's a capital R.